In this exercise, we're given this function y equals f of t, and it's plotted on the y-t-axis. And we're going to assume that the area under the curve from 0 to 1 is the same as the area above the curve and below the t-axis from 1 to 2. And that common area we'll denote by r. Using this assumption and other properties of the function f, we're going to determine a lot about the area function associated with f. Now, what is the area function? Recall that it's the definite integral from 0 to x f of t dt. So it's the area from 0 to some number x, and x is going to be chosen between 0 and 3. First and obvious fact is that if we plug in 0, well, we're integrating from 0 to 0, so of course it's going to give us 0 as the value. And we want to know some other things about the area function. Here are 3 instructions. First, find the zeros. We found one of them. Can we find any others? And can we find local max and min? And finally, can we sketch the graph of A? Okay. So, yes, for number 1 there is another 0, and it's given using the fact that R is the same area from 0 to 1 and then above the graph from 1 to 2. Since this region is below the t-axis, it's contributing a negative area, and that's going to cancel with this positive area from 0 to 1. In other words, if we plug in 2, we're integrating from 0 to 2, f of t dt, and using the notion of signed areas, this positively signed area cancels with this negatively signed area, so we get 0. Thus A has zeros, x equals 0 and 2. Oh, by the way, what is A of 1? Just to see that we're all on the same page. Well, it's the definite integral from 0 to 1. In other words, the area between the graph of the function and the t-axis as t goes from 0 to 1. That's just our value r, which I've denoted as red. So now moving on to number 2, can we determine local max or local min? Here we're going to use the first derivative test and the fundamental theorem of calculus. So what did the fundamental theorem of calculus say? Well, the first part was that the derivative of the area function with respect to x is that integrand f. In other words, the area function is an antiderivative of f. That's how we knew that any continuous function has an antiderivative. It's because we wrote down the area function and we're able to prove that its derivative is f. So what does that tell us now? From Calc 1 we know that whenever a function is increasing, its derivative is positive, and vice versa. So whenever f is positive, the area function is going to be increasing. And we can look at the graph to decide when f is positive. It's positive when its graph is above the t-axis. So this tells us A is increasing, the upward arrow means increasing, whenever the graph of f is above the t-axis. So between 0 and 1, and later between 2 and 3. And whenever the graph of f is below the t-axis, f is decreasing. No, I take that back. F is negative, which means the area function is decreasing. So between 1 and 2, area function is decreasing. So what happens as x passes 1? The area function was increasing and then it was decreasing. Increasing, then decreasing. That means there's a local max. A has a local max where? X equals 1. So then as x goes through 2, a was decreasing, and then when x passed 2, over here a was increasing. So decreasing, then increasing. That means a has a local min x equals 2. And that answers number 2. So finally we can put our conclusions from 1 and 2 together to sketch this graph of A over this closed interval. So I'm going to copy this axis, same y-axis, although now we're actually having x as our independent variable. And that's just the name of the game when you have area functions. F was a function of t, and x was some value between 0 and 3, and that becomes the variable for x, since the variable x was one of the limits of integration. So even though f was a function on the y-t axis, its area function is a function on the y-x axis. Okay. So now we're going to graph A. Let's do the easy stuff first. Where is its zeros? 0 and 2. So that tells us about 2 dots that we can put right here. X equals 0. And x equals 2. And then in the second question we found out we had a local maximum at x equals 1 and a local minimum at x equals 2. So local max at x equals 1. It's somewhat arbitrary where we put the point, although we couldn't put it down here. Why is that? Well, remember, when x is between 0 and 1, a is what? Increasing. So if the area's function's graph starts here, it's got to be increasing, and then at some point it has a local max, and then between 1 and 2 the area function was decreasing till it hit this local minimum, and then the area function was again increasing between 2 and 3. So it looks something like this, and I'm just going to fill in the dots, something like that. So rough sketch of the area function y equals a of x. Some of the main ideas here, again, the fundamental theorem of calculus. The derivative of the area function is the original function f. And we also know from the fundamental theorem of calculus that the area function is continuous and differentiable. And we also use the fundamental theorem of calculus. Knowing when the derivative is positive tells us that the area function is increasing. When its derivative is negative, the area function is decreasing.